begin, I'd like to start by thanking the organizers for the opportunity to speak. So this course is about Iwahori Hecke algebras and their role in the p-adic Langlands program. But for today, I'm going to kind of start from a more general point of view to kind of motivate some of the things that will come later. So the broad goal is to understand the representations of p-adic groups using Hecke algebras. So this is kind of a very broad goal, and I'm going to try to be a little bit more specific about what I mean about representations of p-adic groups, and understand is kind of a vague term, so I'm going to try to make that more precise and tell you which Hecke algebras I mean. Okay, so let me start getting more precise. And as I go on, if my handwriting is not legible, please let me know. So more precisely, I'm going to let, for today, G be GLN QP, so slightly more general than yesterday. I'm equipped with its p-adic topology. So I think of this as a topological group. It's topology inherited from QP. And maybe I'll just say that almost everything I say today is going to apply to a general p-adic group. So if you, say, prefer thinking about symplectic groups or exceptional groups, everything I say today is going to apply in that case. But for the sake of concreteness, I'm going to work with GLN. So I'm just write everything works in more generality. So the statements may have to be modified a little bit, but I'll try to write the statements in such a way that they lend themselves to generalization. And I'm also going to fix an algebraically closed field C, which is going to serve as my field of coefficients. And so the goal that we're after is we want to examine the category rep C of G. And I think this came up yesterday already. And these are just the smooth representations of G with coefficients in C. Okay. And I'm specifically not fixing the characteristic of C for this portion. Later on, C will be FP bar, but for motivation, actually, today I'm just going to work over the complex numbers, because there, things are maybe a little bit more familiar, and we have a few more tools at our disposal to kind of give motivation from. And so I'll just remind you that smooth in this context means that, so maybe let me call my representations V. So for every V and B, the stabilizer in G of V is open in G. So this is some sort of continuity assumption. Okay. So perhaps the first question to ask is, why do we care about this category? And so there's kind of a silly answer, which is, well, we have a group, and so we want to understand its representations. Maybe if we're more representation theoretically inclined, anytime we have a group or an interesting object, we want to try to understand its representation. So I don't find that particularly convincing. So let me give maybe a little bit better of a motivation. So at least conjecturally, the irreducible objects in rep CG, so the irreducible representations of GLN-QP are parameterized by homomorphisms
audio seems to come out. Let's try to speak louder. So homomorphisms from the absolute Galois group QP we saw yesterday to GLN C. So these types of Galois representations. Here, this is often denoted G hat. I mean, it's the same GLN, but it's going to change depending on what my group is. So, for example, if I were to take SLN here, then this G hat will be a PGLN. So there's some sort of duality happening. It just so happens that for GLN there is. So these irreducible objects in here are classified by these Galois automorphisms. So we have what is often referred to as the local Langlands conjecture or local Langlands correspondence. And I should say that this description that I've written is a little bit rough. So even if I take C to be the complex numbers, I need to modify this a little bit. It's not exactly these types of homomorphisms that I think of. So what this does for me, kind of the consequence of understanding this and thereby understanding these types of Galois representations, is that knowledge of this category gives us arithmetic information. So for example, knowing this local Langlands correspondence tells us about higher ramification in this Galois group. So perhaps you've seen that there are these things called ramification subgroups, inertia groups, wild inertia, and so on. And the local Langlands correspondence gives us some information about higher ramification in a very kind of clean way. So that's one consequence of this. Yeah.
Okay. Yeah. Right, so knowledge of this local Langlands correspondence tells me something about higher ramification, so it gives me information about the structure of this Galois group. It also tells me information about the structure of a global Galois group. So if I'm kind of interested in arithmetic things, maybe I want to look at the absolute Galois group Q instead of QP. And so this local Langlands correspondence gives me information about this local picture, And that can in turn be leveraged to give me information about this global Galois group. So, for example, there was a result of Chenevier and Koziol, which told me kind of exactly when this decomposition group injected into a group of this type. So, very classic questions about just the structure of this absolute Galois group came about, the resolution only came about from understanding this local Langlands correspondence. Maybe just finally, I'll just say this a little bit vaguely. This also gives me information about global arithmetic questions. For example, the proof of Fermat's last theorem used various aspects of this local Langlands correspondence. In particular, there's a flavor of this kind of local Langlands correspondence where I take C to be FP bar, and kind of a prototype or kind of initial information about a mod P local Langlands correspondence was used as input in the proof of Fermat's last theorem. So even having some partial information about this Langlands correspondence can kind of have some very good or some very interesting consequences. So this is maybe one reason why we care about this, is coming from these local Langlands correspondences. And another reason, maybe motivated by this first one, is that these representations of G are often, well, they're often infinite dimensional, but they're still very hands-on. So you can actually work with them, kind of get your hands dirty with calculations. So it's a good starting point into kind of understanding this kind of Langlands philosophy. Okay. So this is probably the best motivation for studying this category that I can give, is that we have this Langlands correspondence that's proven in certain cases and conjectural in other cases. But it leads to kind of a tremendous amount of arithmetic information. And this is kind of a good starting point. Okay. So that's maybe enough of motivation. Let me kind of say how we plan to get our hands on this thing. And for today, I'm just going to take the complex numbers. I know this is a program about the p-adic local Langlands correspondence, but I still feel like knowing the complex story is important to have a broad, big picture view, and it's going to kind of help motivate some of the constructions in the p-adic case, or in the mod P case. Okay. So, right. So the question then is, how do we study this category? Okay. So if I just give you something like this, it's maybe a little bit tricky to figure out where to start. And so one strategy is that we can break up, or maybe organize, is a better word. We can organize this category by maybe depth or level. Okay. And I'm using these kind of in quotes because there's precise definitions of what these mean, and I don't necessarily mean the precise definition. But let me indicate what I mean kind of starting with level 0. So what I'm going to do is I'm going to let K denote GLN Z. So this is a group we saw yesterday. It's a pro-finite group. And this is the maximal compact subgroup of G, okay, up to conjugation. Okay. So what I can do is I can consider the following subset of this category rep CG. So let's consider the following subset. So I want to look at representations which kind of behave in a nice way with respect to this group K. And then I'll write down the definition and then give some examples. So what I want to look at is all representations V, and maybe let's just stick to irreducible representations of G satisfying VK is non-zero. Okay. So we saw this notation yesterday, but what this means is just a set of vectors in V that are fixed by the entire subgroup K. So such that K dot V equals V for every K. So such representations are often called unramified. Or sometimes spherical. So all it means is it's a representation that has non-zero vectors fixed by this maximal compact. Okay, so this is some definition, some subset. So let me give you examples of what, well, I won't classify these, but I'll give you a bunch of examples of what these things can look like. Okay, so this set contains the following representations. So a very kind of easy example that one often looks at first is the trivial representation. Okay. So that's just the one-dimensional vector space, C, with G acting on V is equal to V for every V and D and G and G. So it's a one-dimensional vector space, it's irreducible, and the entire group G acts trivially. So in particular, the subgroup K will also act trivially. Okay. So this is not particularly exciting, but it's well, it's the first example of a representation that I've written down. So that's one example that lives in this set. Let me give another example. So this one's going to be for n equals 2. So let me take, so this is what is called an unramified principal series. Okay, so we saw some examples yesterday of these principal series representations that come by parabolic induction. I'm going to give kind of another model for it. So I'm going to take B to be the locally constant functions on P1 or QP, valued in C. So again, this is just all functions from the projective line to C, which are locally constant. So that's the space. And I need to tell you how GL2 acts on this. So if I take A, B, C, D, and I act on F, so I'm supposed to get another function from P1 to C. So I should tell you what it does on homogeneous coordinates, x, y. And the way this is going to act is as follows. I've got my coordinates correct. So it's dx minus by and minus cx plus ay. Okay. So this is for every a, b, c, d. GL2QP. And F and B. Okay, so let me unpack this a little bit. So P1 is just, well, the projective line, and this has an action of GL2QP by Mobius transformations. It's the same way you would see, for example, in complex analysis, you have, instead of P1, you have the Riemann sphere, and GL2C acts on that by Mobius transformations. So this works much more generally. You can put QP here. And so I have an action of ABCD on XY, and to get an action on functions, I just have to do some sort of inversion here. But this gives a well-defined action. And as it turns out, this is an unramified representation. So this V is an unramified representation. So what that means is that there's some function that's fixed by GL2Z. So i.e., there exists an F such that maybe non-zero F, such that Kf is equal to F for every K. Okay. So this function is unique up to scalars, and maybe I'll leave it as an exercise to find this in it. It's not too difficult to kind of think about what's going on. Okay. So even though this doesn't look like a parabolic induction, like what we saw yesterday, it is isomorphic to a parabolic induction from the Borel up to the group G. This is just a different model for it. Okay, so any questions on these examples?
So example 1 is hidden in example 2, right?
Sorry?
And example 2 works because of example 1, right?
How do you mean?
I mean, we even have a G fixed vector, right?
No, I don't think there's any G fixed vector. No, you might be right. Yeah. So there should be a G fixed vector. But if you know the answer, don't give it away.
No. Is there a genuine example in which there is no G fixed vector but there is a K fixed vector?
Yes. You can take just a non-trivial character that's unramified. You can already see it for GL1. If you had a G fixed vector, then you'd have to have a trivial character. But you can just take a character that's trivial on the maximum compact.
Nothing to do with n equals 2 us.
Yeah, so this doesn't have anything to do with n equals 2. I could do Pn minus 1 here. Yeah. Other questions? Okay. So, this is some subset of representations. And again, we want to study the category of all representations, and I'm kind of claiming that we can start with this. So the question is, how do we study these V's with VK non-zero? Okay. So I'm going to tell you 3 facts, which I'm not going to prove because it's a little bit outside of what I want to do, but I'm going to tell you 3 facts about what we can do in this setup that's going to give a way of understanding these representations, and at the same time it's actually going to construct the local Langlands correspondence. So here's fact 1. So I'm going to do this out of order. So if V is irreducible and VK is non-zero, then the dimension of the space of invariance is actually equal to 1. Okay. So again, all these facts are very much non-obvious. So again, today's lecture is more about motivating things and not proving too much. But it nevertheless is true. It doesn't require too much, but going through the proof would take me a little too far afield. But if you want a reference for this fact, there's a wonderful book by Bushnell and Enyart about the local Langlands correspondence for GL2, and this is proven in that book. Okay. So in fact, if I have an unramified representation, which is non-zero and irreducible, then its space of invariance is actually equal to 1. Okay, so we know a little bit about this vector space now. Yeah, I guess in this example, this V is actually not irreducible. It's reducible, so maybe keep that in mind if you're trying to find this. But it's still true that its space of K invariance is one-dimensional.
And this fact works with some more groups than GL?
Yeah, so this fact works for any group G and any, I guess, hyperspecial maximal compact. So if you like, for example, symplectic groups, you can just take SP2N in the ZP, and this still works. Okay, so fact 2. So the way you should think about what's going on here is that I have these sorts of irreducible representations. And I kind of mentioned it in passing, but in general, these V's are going to be infinite dimensional. So there's very, very few instances where the irreducible representations will be finite dimensional like this one. So in general, we're dealing with infinite dimensional things, but this is saying, if we look at K fixed vectors, as long as it's non-zero, it can only be one-dimensional. So I'm kind of shrinking from an infinite dimensional thing to a finite dimensional thing in a very controlled way. So as it starts out now, this V to the K is just a vector space, but in fact, this VK has an action. So it's not just a vector space, it actually has some more structure to it. So it has an action of the following thing. So this is where Hecke algebras start to come in. So this is the notation I'm going to use, HGK. And what is this? This is the set of all functions from G to C, such that F is compactly supported. and it's invariant by k on both sides. So f, k, g, k prime, f, g, for every k, k prime and k, g and g. And this is what is called a spherical Hecke algebra. Okay. So we saw a version of this in Professor Gatte's lecture yesterday. There he was using kz, kz. There's not too much difference in what I'm doing here. And this corresponds to taking the trivial weight. So if you unravel all of those definitions that you saw yesterday, this is the kind of thing you get. So this is an algebra, so I should say that it has something called a convolution product. Which I'll describe a bit more later. I don't want to get into it too much. Okay? So not only is this VK a one-dimensional vector space, but it actually has an action of an algebra. So like the fact that there's this G here means you haven't forgotten about the G action.
So this is compactly supported modulo K or just compactly supported?
Well, K is compact, so they're equivalent. So if you think about it as functions on the double cosets, then it's finitely supported. Okay, so we have these two facts. There's a third fact, which is maybe the most kind of intricate of all of them. But again, it's completely analogous to something we saw yesterday. I can actually describe the structure of this algebra. So back 3. So we can describe the algebra structure of HGK as follows. So again, these functions are compactly supported and k-by invariant. So for example, I have something like, if I look at the characteristic function of k, that is an element here, it's compactly supported and k-by invariant. Or I could take something like the characteristic function of k, p1k. This is a double coset. It's compact as a set and k-by invariant. So, etc. All of these are in this Hecke algebra. Okay. These are examples of compactly supported functions that are k-by invariant. But just because I've written this down, it's not clear how I take the product of two of these under this convolution. So this fact number 3 is going to make that a little bit more clear. And the way I do this is with the Satake transform. So what the Satake transform says is that I have an algebra isomorphism. So this is an algebra isomorphism to an analogous Hecke algebra on the torus. Okay. So this T is the maximal torus that we saw yesterday. Okay. And so I won't give the precise definition, but if I look at n equals 2, I can actually write down some examples of things and where they go. So if I were to give you the formula, sorry, there should be a W here, which I'll explain in a moment. So if I were to give you the formula, one could work this out. If I have this characteristic function, this goes to the characteristic function of t intersect k p1 plus the characteristic function of t intersect k 1p, except I have to multiply this by p to the 1/2. Another example, if I take something like the diagonal central element, pp, then this goes to just the analogous thing. On the torus. So this is very, very explicit. And again, if I were to tell you what this does, then you could just sit down and work this out. It's not really the main focus of what I want to do. I just want to kind of indicate that there is this thing called the Satake transform, which gives you a precise structure of this Hecke algebra. So because this is an algebra isomorphism, it means that the product here respects the product here. And since T is a commutative group, that means that this is going to be a commutative algebra. So what it says is that this algebra is actually commutative, which is not really obvious from what I've given. Even if I did write down the convolution product for you, it wouldn't be obvious that this HGK is commutative. Right, so we have this description, and I want to kind of modify this description a little bit. Oh, and I should tell you what W is. And all of these things I'll explain kind of in more detail a little bit later. So this W is just the symmetric group Sn. And it acts by permuting these coordinates. So I should say, moreover, this Hecke algebra is itself isomorphic to an algebra which is much more familiar, and that is just the group algebra of T mod Tk. This is not so hard to see, and again, it follows from the fact that T is commutative. Okay. And so here, the product is literally just the multiplication you would see in the group algebra. And I have to just look at the subset of things which are invariant by this symmetric group action. Yeah, so let me leave it there. Okay, so I have these three facts, and what I will do next is combine them to kind of indicate how we can study these representations. It won't give a precise construction, but it can help us to kind of think about what's going on. So, I'll do that here. So, if I have an irreducible V with Vk non-zero, well, this fact 2 tells me that that corresponds to Vk with an HGK action. So a module over this this algebra. Fact 1 says, well, this is a one-dimensional vector space. And so what is a one-dimensional vector space with an action of an algebra that's the same as an algebra morphism? So this is the same as an algebra morphism. HGK to C. If I give you such a thing, I can construct a one-dimensional vector space C with the action of HGK given by this morphism. Yeah, I guess I should have said maybe I'll just kind of say this here, that this procedure gives me a bijection between irreducibles so maybe let me just say this kind of out loud. So somewhere buried in these facts is that if I have such an irreducible with non-zero invariance, I get a non-zero module over this thing, which is simple. And conversely, if I have a simple module over this HGK, that corresponds to an irreducible. So these irreducibles correspond to algebra morphisms, and by this third fact, well, this HGK is isomorphic to this thing, and the Hecke algebra of the torus is isomorphic to this group algebra. So this corresponds to an algebra morphism C T intersect K W to C. Okay. So the next step requires a little bit of a maneuvering, but what one can show, so now I have an algebra morphism between two C algebras. So if you like, if you're used to some algebraic geometry, this corresponds to a point in spec of this ring. But what it means on a more kind of down-to-earth level is it corresponds to an element t hat of what I'm going to write as T dual C. So this is the torus in G hat dual to T. Okay. So, but what this is just n copies of C star. Up to, maybe I should be a little bit more careful. The fact that I'm taking these W invariants here means that I'm taking this kind of up to permutation again. But what I can do out of this, and this is the kind of the final step, is I can actually cook up finally a Galois representation. So I can cook up morphism from the Galois group QP bar. So how did I do this? So this surjects onto the subgroup generated by the Frobenius element. And what I can do is I can further map this into GLNC by taking this Frobenius element to this T hat. Okay. So this composite homomorphism gives me a Galois representation. Kind of the simplest Galois representation we can think of. Okay. So again, we saw it in Professor Gratze's lecture yesterday that we have these kind of mod P Galois representations. And this is kind of an even simpler version of that. So there's nothing happening with this kind of QP squared extension. This is just kind of much more down to earth. I have this Galois group that surjects onto the subgroup generated by this Frobenius element. And since this is a subgroup generated by one thing, I can just map this Frobenius element to this T hat that I constructed. And if I compose the whole thing, I end up getting a morphism from the Galois group to GLNC, which is the Galois representation associated to the initial V that I started with. So this is kind of a long-winded way of saying that using all of these structural properties, which again, I've kind of given you on faith, one can construct instances of the local Langlands correspondence. And in fact, for global questions, say about modular forms, an understanding of this unramified case is kind of the most important thing. Because very often we're matching some sort of Hecke eigenvalues, so some eigenvalues of the spherical Hecke algebra on this side with Frobenius eigenvalues on this side. And this is a way of doing that. So again, this section is maybe a little light on details, but it's designed to kind of give you an idea that the more structural results we get, the kind of closer we are to making some sort of Langlands correspondence. Okay. Okay. So are there any questions on this? From here to here? Let's talk about that after, because it requires a little bit of diversion into talking about these Langlands dual tori, which I don't really want to do right now. But maybe the best thing I can say is that if you've, again, seen any kind of algebraic geometry, you might have seen this thing called the spec construction, if I have a ring. So if I look at what an algebra morphism means, this gives me a maximal ideal in this ring. So it gives you a point of the spectrum of this. And it turns out that the spectrum of this ring is exactly this torus here. Yeah, that's a good point. The K goes away. That reason's easy. This gives me an element really up to Sn actually. Okay, anytime I consider Galois representations, they're always up to conjugation. So really, I should get a Galois representation up to G hat conjugation. So that's why the W goes away. Okay? And for the K going away, that kind of comes from going from here to here. It's kind of fitted in there. Okay. I'm sorry?
Focus on the fixed vectors.
Mm-hmm.
It's giving you a Langlands
Yeah.
tendency. But would it give more information about V itself?
So we'll give you information about how the Hecke operators act, and often this determines the representation. So what these arrows show is that if I have some mystery representation B, and I know how the Hecke operators act on this space, well, then there's only one representation that could satisfy that property. So if you give me such an algebra morphism, then what I can tell you is that there exists a unique representation that has this as its set of parameters, but actually constructing it, like constructing a physical vector space, might take a little bit of work. Yeah. But you know that if you manage to do it, that's the only one.
Isn't that the tensor product with the complex
I'm sorry?
V is compactly induced representation times VK over conjugate.
Yeah. So that I'll probably mention a little bit in the second lecture. But this I kind of wrote in the most transparent way possible. I mean, here we just have functions that satisfy some transformation conditions. But this thing you can think about as endomorphisms of some compact induction, like we saw yesterday. So it really is the same kind of thing. And these invariants are, again, going to be some homomorphism of a compact induction entity. So I'll probably discuss that tomorrow. Okay. Other questions? All right. So let me go on. So I should say, maybe this was a little bit fast if you haven't seen it, but I'll start to give more details next lecture. I just wanted to indicate kind of what is known and what it's used for. And the fact that we can combine these three facts together to get an instance of the local Langlands correspondence is already quite powerful and quite useful. And so let me indicate what happens if we want to go further. So I'm going to go now to level 1. What do I mean by level 1? Now I'm going to let I denote the Iwahori subgroup. G, which I can think of as the preimage of, well, BP was the notation that was used yesterday. In GLN FP under this projection. And for GLN, we can actually see what it looks like. It's just all matrices that have ZP cross on the diagonal, anything I want in ZP above, and PZP below the diagonal. So again, there's a few ways to think about it. I can just take things that reduce mod P to something upper triangular, or more explicitly, things that look like this. Okay. And now what I'm going to try to do is imitate as much as possible what we did here with the spherical case, with this Iwahori case. So first, I'm going to kind of look at a specific subset of this category.
That's just a polynomial algebra in variables, right? This thing on the left.
Yes.
The CT quantity.
Yeah.
So to answer this question, maybe just if I can put in a comment.
Please.
So this thing is just a polynomial algebra in n variables. This algebra, to give an algebra homomorphism from that to C is the same as giving a group homomorphism. I mean, just taking the variables to non-zero things, right? So that's all he's doing, is taking the variables to n non-zero things.
Yes, still, why the K is not there, I don't see.
That
The W I can see because that is the ring of invariance.
So if you,
So that's like the quadrant ring of the quotient variety using by SNP.
so if here's maybe another way to think about it. So T mod T intersect K is just a bunch of copies of this, of QP mod ZP, and this is isomorphic just to Z. Okay? So what is here is just a bunch of copies of Z. So this, before I take W invariance, is a polynomial algebra with maybe plus minus the polynomial variables because of this Z. Okay? So that's what the K does, is it allows you to go from QP to just Z. And so this becomes a polynomial algebra with things inverted. And to give a morphism here, as Mr. Galte said, it's just giving an n tuple of complex numbers, which are invertible. That's where the plus minus comes from. And this W means I look at an unordered tuple. And that corresponds exactly to something like this. If you dig into it, it becomes quite explicit. Okay. Right. So now we're dealing with this Iwahori. It's a slightly smaller subgroup than K. And we want to consider, again, the following subset is with E-reps would be of G satisfying V to the I, which is not zero. Okay. So obviously if I have a K invariant vector, it's also going to be I invariant, so this contains everything we've already done. So this contains the previous representations, but it contains more. So here's an example, again for n equals 2. So I'm going to define the Steinberg representation in a bit of an unorthodox way. I'm going to take this last example that I did of locally constant functions on P1. And this has a G-stable subrepresentation which consists of the constant functions. I can just look at constant functions on P1 to C, and that is G-stable, so I'm going to divide by the constant functions. So I take this quotient representation, and I get this thing called the Steinberg representation. And it turns out, which is not obvious, that this is actually irreducible, and it is not K invariant. So this thing has an action of GL2QP. Then ST is irreducible satisfies STK equals 0, but STI is not 0. Yeah, and I should say it's called the Steinberg. It's ubiquitous in representation theory. And again, other examples are a little bit harder to write down, but this is kind of the first example of what is called an Iwahori spherical representation. And again, this is not any sort of defect, it's just a fact of this representation. And again, it's a little bit of a different model than what we saw yesterday, but it's equivalent. Okay. So we can look at this subset of representations now, and as before, if I have such a representation, the space VI has an action of HGI. It's a shame I erased it, but the definition is going to be exactly the same, except I'm going to replace K with I everywhere. So this is all functions from G to C, which are compactly supported. And such that f I g I prime is f of g for every I prime and I, g and g. And this is called the Iwahori-Hecke algebra. Right, maybe I'll write here. This also has a convolution product. So analogous to whatever the convolution product on the spherical Hecke algebra was. I'm not going to write it down right now because we're not really going to use it. Certainly not today, but in the next lecture, I'll kind of write down explicitly what this product is and have an easier way to think about it. So this is somehow the main thing that these lectures are going to be about, is this Iwahori-Hecke algebra. And why like an entire lecture series about just these algebras? Well, I'll try to kind of motivate that in the time I have left. I mean, the short answer is that this spherical level is already kind of well understood, and we've kind of squeezed all the juice we can out of it. But there's a little bit more to say with this Iwahori-Hecke algebra, and there's a little bit more interesting structure that's going on. Okay? So one thing I'll note is that, and this is not an obvious statement, but this HGI is not commutative. Kind of contrary to what happens with HGK. This statement is not obvious, but we'll see in the next lecture why that is. But we still have kind of an explicit description of its structure. Meaning, we can write down a basis fairly easily. We can write down a set of generators as an algebra. So analogously to how in the spherical case we had these polynomial generators, symmetric polynomials, we'll be able to write down generators and we'll be able to write down relations. So it's a very kind of beautiful structure theory that I'll describe probably next time. Moreover, if V is irreducible and VI is non-zero. So again, we have some analogous fact that I maybe said out loud for the spherical case. Then VI is a simple module over this Iwahori-Heck algebra. Okay. Which again follows from similar reasoning, but so this says if we're thinking about irreducible representations that have I fixed vectors, then it suffices to look at the simple modules. And there's a one-to-one correspondence between these. I guess the difference now, though, is we could have, well, yeah, maybe the more precise way is that the dimension of this VI is bigger than 1 in general. So we've sort of lost this dimension 1 property, but this thing is still a finite dimensional module over this. So we're kind of converting an infinite dimensional problem into a finite dimensional problem. Okay, so it's a finite dimensional vector space with an action of this Heck algebra. Right, and so I don't really want to kind of say any more, but maybe I'll say out loud. So there is a lot of structure theory, kind of analogous to these 3 facts that we had for the spherical Heck algebra. And these 3 facts for the spherical Heck algebra allowed us to kind of build a Langlands correspondence. So it takes a lot more work, but you can do something completely analogous for the Iwahori-Heck algebra. So this uses results from geometric representation theory, but you can actually build a Langlands correspondence for these representations. The result is no longer these unramified Galois representations, but it's some kind of more general class of representations. So by understanding these things and the structure of this new Heck algebra, we can still get instances of Langlands correspondences. So maybe I'll just kind of write that. So in both K and I cases, the procedure of passing to HGK or HGI modules allows us to build kind of explicit instances of the local Langlands correspondence in a way that's kind of uniform. So, so for example, if you look at the book of Bushnell and Yerrick, they construct the local Langlands correspondence for GL2, but a lot of the techniques only work for GL2. Using this kind of approach with this kind of Satake thing and passing to modules over this Iwahori-Heck algebra, we can build more instances of local Langlands correspondences. And this kind of machinery works for general reductive groups. So it's not specific to GLM. I could have done this whole thing with a symplectic group or an exceptional group, and everything carries over in exactly the same way. So this is why this is such a kind of powerful method is we can build these local Langlands correspondences for kind of many groups at once. But there's actually somehow an even better consequence of this. So in the Iwahori case, this bijection between eReps V with VI not 0 and simple HGI modules. So this bijection actually comes from an equivalence of categories. Comes from an equivalence of categories. Okay, so here's the theorem due to Borel and Bernstein, I guess. Elaborate. But what does this say? It says the following. So if I look at the following subcategory, so let's say I start with my rep G, and I put an I here. So what is this? This is the set of all representations. Okay, not necessarily irreducible, such that the following holds. So if I look at the I invariant vectors in V, and look at the G representation generated by that subspace. So this will be some sub-representation of my original V, and I'm asking for those representations that actually give me V back. So it's all, so otherwise said, it's all representations V, which are generated by their I invariant vectors. If I look at those representations, so I can take those and map it over to HGI modules. And so this map just sends V to VI. So if I look at this thing, so not on the entire category, but on this subcategory, this is actually an equivalence of categories. So if I had told you this statement right from the beginning, the fact that it's an equivalence of categories just immediately implies this. If I have an irreducible representation that has VI non-zero, then this thing will be a sub-representation. Since V is irreducible, then I'm forced to have inequality. So yeah, so what this says is not only am I kind of matching the simple objects, like the building blocks, I can actually kind of really beef it up to like identify the categories. Okay? And the consequence this has is that this category, which is maybe complicated, I don't understand it, at least a chunk of it, I can understand as modules over some ring. Okay, it's not commutative, but it's still like a module category over some ring, which is incredibly useful. I have, when I'm, if I'm doing kind of algebra over rings, I have things like projective modules, injective modules, and this says that I can transfer all of that information back here. So it gives me a good amount of information about this category. yeah, maybe I'll just say this out loud instead of writing it down. This thing is actually a block of this category. So the category of smooth representations kind of decomposes into chunks, and this is a particular block. But what it says is that basically anything I do in this category is the same as doing it in this category. So this is kind of the thing I want to focus on, is that, you know, understanding this category that I said at the beginning, at least a good subset of it I can understand by using Iwahori hypermodules. And this is what we're going to try to imitate in the mod P case. And I will say kind of when it works and when it doesn't, and what kind of consequences we can draw from it. Okay. Let me finish with a few comments. Right. Yeah, some comments. So, this equivalence gives info about rep CG. Okay. So, questions about representations here, I can just obtain by transferring them over. So just to give an example, if I wanted to calculate something like an X group between two representations, well, this could be very difficult. So, I mean, this is something I'll talk about later in the mod P world. Like, calculating X groups can be quite tricky. If you ever try to do it for just regular rings, you have to do this whole business where you write down injective resolutions. And if I give you kind of an arbitrary representation, then writing down an injective resolution can be kind of a nightmare, especially because these two probably are infinite dimensional to start out with. But what this equivalence of categories says is that I can essentially transport this question to the other side and calculate xn in the category of modules over this ring, vi, v prime I. Okay, so what have I done? Well, I've just kind of transferred things across this equivalence. Here, I have kind of an honest to goodness ring. I don't have to think about, what does it mean to be smooth? Well, if I take an extension, is it smooth or not, etc. I can just look at kind of all possible modules over this ring. And these two objects are very likely finite dimensional. So now I'm just looking at extensions over of finite dimensional modules over some ring. So this is presumably an easier question to answer. I'm sorry?
It will be only a containment, right? The left-hand side could be treated. Because there may be, at least it's not obvious that there may be an extension that is not every variable.
I see. Well, I think this maybe comes from the fact that this is a block. Yeah. Yeah, in the complex case. Yes, yes, yes. Yeah. Yeah. I mean, what you said is a very non-trivial fact, and like I said, we're quoting results of Bernstein, which are in general very, very deep. So, yeah. Right. So I have something like this, and maybe just another comment is this equivalence. Is not true. Okay. So I'm really using something about the Iwahori subgroup to get this equivalence. For K, we have a lot of nice features. I have this commutativity, I have this Satake thing, but I don't have such an equivalence of categories. If I were to write K here and put the spherical Hecke algebra, it's no longer an equivalence of categories. And I can, maybe say more about that later. Okay, so this is kind of very useful, and as I said, next time I'll actually start talking about mod P things, or maybe just secretly talk about mod P things. And we're going to kind of see an analog of this theorem in the mod P case. And maybe just to kind of conclude, I'll say, so I did like this level 1 thing, level 0 thing, and you can ask what happens for higher levels. And again, I don't mean this in any kind of precise technical sense, but higher levels, if I want to kind of think about pushing this kind of equivalence further, or going deeper into some filtration, I'll just say that this kind of leads to the theory of Bushnell-Klitschko types. Which is some sort of generalization of this when you have a smaller subgroup and perhaps with some sort of weight. But I don't really want to comment on that. If you are interested, this is the key word to Google. Okay, so I think this is where I'll stop for